Hi, my name is Neil Vore, and I'm an 8th grade student at Cuesta Elementary School in Mountain House, California. I joined the YRI Fellowship program because I'm passionate about learning, research, and sharing ideas that can make a positive impact. One of my biggest goals is to publish my own research paper and develop skills in critical thinking, problem solving, and academic writing. The fellowship gave me an opportunity to work with mentors, explore real-world topics, and improve my ability to communicate ideas clearly and confidently. I believe this experience will help me grow both as a student and as a future leader, while allowing me to contribute meaningful work through my research and publications. Good afternoon, everyone. My name is Neil Vore, and today I'm presenting my project, AI-based nail disease classification using image characteristics and deep learning. Before I begin, I want to sincerely thank the YRI Fellowship Program for the opportunity to work on this research. I also want to thank my mentor, Dr. Aishwarya Tomar, for her support, feedback, and guidance throughout the project. Her help made a big difference in shaping this work. Now, let me start with a question. When you look at a nail image, how easy do you think it is to tell whether it is healthy or not? For most people, that is not easy at all. Even for trained professionals, nail disease diagnosis can be difficult because the signs can be subtle and different conditions can look very similar. That challenge isn't what motivated this project. Now, manual examination of nail anomalies can be highly subjective, time-consuming, and dependent on clinical experience. That basically means two people may not always come to the same conclusion when looking at the same image. One person may notice a pattern, while another may focus on something else. In a busy setting, that can slow things down even more. This is why the project focuses on a computer-based method. The goal is not to replace doctors, but to support them with a tool that is more consistent and data-driven. In other words, we wanted to see if AI can help reduce variation and improve screening. To test that idea, the project used a structured workflow. The first step was pre-processing. The images were resized to 224 by 224 pixels and normalized. Contrast and intensity were also adjusted to reduce lighting problems. That matters because medical images can vary a lot depending on the camera, the light source, and the environment. If those differences are not handled well, the model may learn the wrong things. The second step was the baseline model, which was logistic regression. I like to think of this as the simple test model. It's fast, efficient, and useful as a starting point, but because it works on flattened pixel data, it does not naturally understand spatial patterns in an image. The third step was ResNet 18, a deep residual CNN. Unlike logistic regression, ResNet 18 works directly with image tensors. That means it can learn shapes, textures, and deeper visual patterns much better. Since nail disease signs can be small and detailed, this kind of model is a better fit. Now onto the model formulation. The difference between the two models is very important. Logistic regression is a convolutional baseline. It maps simplified pixel values directly to class predictions using linear equations. That makes it easy to use but also limited. It struggles with complex texture, shape, color variation, and diagnostic shifts. Now, ResNet 18 works in a very different way. It uses convolutional operations plus residual connections to learn structural details from raw images. The residual design helps the network avoid problems like vanishing gradients, which can happen in deeper models. That allows the model to stay stable while learning more complex patterns. So, if you compare the two, the baseline is like looking at a picture in a very flat, basic way, while ResNet 18 can actually study the visual structure in much more detail. Now, the experimental settings. To keep the experiment fair, several settings were controlled carefully. The target resolution was 224 by 224 pixels, which matches standard ResNet input sizes. The optimization target was cross-entropy loss, which is a strong choice for classification tasks. The batch size was 32 images per iteration, which gives a good balance between memory use and training stability. The learning rate was 0.001, which helps the model from taking steps that are too large during training. The full run used 5 epochs, which gave a consistent training period for comparison. Why does all of this matter? Because if the setup is not controlled, then the results are harder to trust. By keeping the same conditions, the comparison between models becomes much more meaningful. Now onto the comparative results. Now let's talk about the results, because this is where the difference becomes very clear. ResNet 18 achieved a major improvement over the conventional baseline logistic regression. It reduced total evaluation errors from 56 down to only 4. That's a very large drop in error, and it shows that the deep learning model understood the data much better than the linear baseline. If we pause and think about that for a moment, that is a strong result. It means the model did not just do slightly better, it did much better. And in a medical setting, that kind of improvement can matter a lot. Now, the classification power. The test set accuracy reached 98.7%, which is extremely strong for this type of task. Now, what does that tell us? First, the model was able to separate classes well, even when the image textures were complex. Second, it handled minor color changes without losing performance. Third, the learning process remained stable, with no major degradation issues. That makes the model promising as an entry-level screening support tool. It may not make the final medical decision, but it can help identify which causes deserve closer attention. Why did ResNet 18 succeed? There are a few reasons why ResNet 18 performs so well. One reason is direct feature extraction. Instead of relying on land-made image features, the model learns directly from source images. That reduces human bias in the feature design process. Another reason is the residual skip connections. These connections let information bypass some of the usual layer-by-layer decay, which helps the model stay stable and train effectively. A third reason is subtle texture capture. Nail diseases often show very small signs at early stages, such as tiny color changes or surface differences. ResNet 18 is much better at catching these patterns than a simple linear model. So the success of the model is not accidental. It comes from the way the architecture is designed to handle difficult image tasks. The clinical translation. Now, let's move on to the clinical side. The most important point is that this kind of AI should be used as a supportive screening assistant, not a substitute for a specialist. That distinction matters. AI can help speed up review and highlight possible issues, but the final decision still belongs with trained medical professionals. This kind of model can be very useful in telemedicine. For example, if someone in a remote area uploads a nail image, a lightweight version of the system can help with first-pass screening. That can make care more accessible and reduce delays. It can also help in busy clinics by giving doctors a second opinion or helping sort cases by urgency. In this way, the model supports clinical workflow instead of just replacing it. Now, coming to the future work, there are still some important next steps. One major issue is dataset leakage. If the same patient's images appear in both training and testing, the results may look better than they really are. To fix that, future work should use patient-wise and source-wise partitioning. Another important step is telemedicine integration. A lighter version of the model could be deployed on remote or edge devices, which would make it practical in real-world settings. Now, to conclude, this project shows that AI has strong potential in nail disease classification. The deep learning model performed much better than the baseline, and the results suggest that ResNet 18 can be a useful tool in image-based screening. Once again, before closing, I want to thank the YRI Fellowship Program and my mentor, Dr. Aishwarya Tomar, for their support and guidance throughout this work. Now, thank you for listening. How do you see AI transforming diagnostic medicine?